Hello everyone, my name is Megan McGillen and I am a fourth year PhD candidate at Cornell University. I am here to talk about the use of protective cultures as a creative microbial solution to the limitations of high pressure processing. High pressure processing offers a non-thermal processing alternative to traditional preservation techniques, satisfying consumer demands for fresh-like and minimally processed foods while extending the shelf life of the product. For food processors, this method can be implemented following packaging, thus reducing the risk of secondary contamination. Unfortunately, HPP's indiscriminatory inactivation of vegetative cells becomes a major limitation for products containing functional microbes with desired biological activity, such as lactic acid bacteria. There is also concern regarding undesired spore-forming organisms which can survive high-pressure processing. This is especially a concern with low-acid foods, such as milk, which has a pH above 4.6. At this pH, outgrowth of pathogenic spore formers like Clostridium botulinum become a legitimate food safety concern. So between HPP, functional cultures, and spores, we have a problem. Which brings us to the main question this work attempts to solve, which is how can we configure a HPP food system that enables the selective growth of desired functional cultures while also inactivating pathogens and spoilage organisms. The solution we came up with centers around encapsulating freeze-dried cultures in cocoa butter. Specifically, we developed a cocoa butter encapsulation system for freeze-dried protective cultures that can be used in combination with HPP without detrimental effects on culture viability or acidification capacities. Why freeze-dried cultures and why cocoa butter? Let's start with the first one. Remember, HPP is only lethal to vegetative cells, hence why spores are such a major issue. For that reason, we believe that the protective effect of spores against HPP may also apply to freeze-dried cultures. And we were right. Using commercially available freeze-dried cultures, we were able to demonstrate their ability to survive HPP when freeze-dried, and their regained susceptibility to HPP when hydrated in advance. Although there was a significant 1 to 2 log reduction compared to the positive control, the overall takeaway is that the freeze-dried cultures maintain high counts even after HPP treatment. As promising as these findings are, their application in something like milk would be useless. Therefore, an encapsulation system is essential for delaying the migration of moisture from food into the desiccated cells, which is where cocoa butter comes in. In this second aim, we wanted to develop a novel encapsulation system that renders any freeze-dried cultures resistant to HPP, regardless of the culture's pre-existing sensitivity to pressure and the food product's water activity. To achieve this, commercially available freeze-dried cultures were encapsulated in cocoa butter by homogenation prior to HPP, resulting in cocoa butter encapsulated freeze-dried cultures. Using the model's predicted optimal factor levels, the encapsulation process was shown not to impact cell viability, with the encapsulated cultures yielding similar counts to those of the non-encapsulated controls. So with these encapsulated cultures in hand, we tested their effectiveness in both a simple buffer and skim milk. Mimicking realistic pre-treatment storage times, the encapsulated samples were immersed in either a simple buffer or skim milk at 24 and 4 hours before HPP. And what we saw was that the encapsulated cultures maintained high counts post-HPP despite immersion in PBS or skim milk for up to 24 hours prior to treatment. The liquid medium or pretreatment immersion period had no significant effect on counts within the encapsulated samples. Acidification of the food matrix is one of the inhibitory mechanisms provided by the protective cultures used in this study. To ensure that the treated cultures maintained the protective effect, pH and counts were monitored over 48-hour fermentation. Pre-immersion times of the encapsulated samples only had a significant impact on pH initially. However, by the end of the fermentation, there were no significant differences in pH across the encapsulated samples and the positive controls. Likewise, the counts for the encapsulated HPP-treated samples differed significantly initially between each other and compared to the positive controls, but lost significance by hour 48, with the encapsulated samples and the positive controls all falling within the range of 9 to 10 log CFU ml during this time. Collectively, we present a proof of concept encapsulation system for freeze-dried cultures that can be used in combination with HPP without detrimental effect on culture viability or acidification capacities. This work addresses the need for HPP food systems that enable the selective growth of desired functional cultures while also inactivating pathogens and spoilage organisms. As such, the system could be used in HPP-treated low-acid foods to inhibit spoilage or pathogenic spore formers through the use of freeze-dried protective cultures. Additionally, the system could be applied to probiotic and/or fermented foods with the intention of making viable cultures and HPP-treated products. Thank you so much for your time, and please feel free to reach out to me if you have any questions.